Good afternoon, ladies and gentlemen. It is a privilege, as always, to participate in GTT's user meeting. I will share with you on the topic of accelerating material calculations for large-scale DRI smelting furnace models and the progress that we've made with RapidThermo most recently. I think we all know that climate change is a big part of the public narrative at the moment, and that we need to turn around temperature increases globally. Also, the iron and steel industry is one of the major contributors to CO2 emissions into the atmosphere, and it has been legislated in several countries to substantially reduce CO2 emissions by 2030 and then even target net zero at 2050. And the steel industry can make an important contribution to this. Now, one of the new green steel making routes is direct reduction with hydrogen or natural gas, melting down the DRI in an electric arc furnace and then going to secondary metallurgy. This route is well suited for high-grade iron ore, and it is a low-risk first step towards green steel making. But it is not cost competitive in the long term. It cannot produce all the required steel grades for advanced applications like automotive. For this reason, we need a new route that is better suited to low-grade ores. This route, unfortunately, has a low technology readiness level and is therefore high risk. But in the long term, it will be more cost competitive because of the abundantly available low-grade ores around the world. And this makes it an inevitable reality, and also confronts us with the concept of DRI smelting furnaces. Now, what are they? These furnaces, this is one impression of what they can look like. These furnaces have to melt and finally reduce the DRI produced by natural gas or hydrogen to produce hot metal, similar to what the blast furnace does, slag, similar to what the blast furnace does that can go to the cement industry. The furnaces and the route as a whole must also compete with the blast furnace in terms of energy efficiency and iron recovery. Now, this is no mean feat. It's a really challenging task. Our current reality is therefore that we need to develop new technology for DRI smelting furnaces. We've got limited time, and we need to make substantial changes or at least progress by 2030. And computational methods can help and support us to accelerate this technology development process. And the most fundamental constraint in our ability to describe high temperature processes with computational models is our ability to describe materials accurately and efficiently. Now, with this as background, I will talk a little bit about the computational realities of material calculations, efficient material descriptions, and then RapidThermo progress. If we think about including detailed material calculations into CFD or multiphysics type models like those we build with OpenFOAM, then we need to be aware that these are the elements that we would want to consider. I'm even excluding a few here, and there can even be more. Now, in this example, we've got 14 dimensions with temperature, and if we take this 14-dimensional phase diagram and we pre-populate it, we pre-calculate it with 25 data points in each dimension, composition and temperature. This can result in a total amount of data between 17 and 144 terabytes. Now, what does this tell us? It's that pre-calculating and training an artificial neural network is perhaps not practical at this point. Also, when we add more and more elements to a CST file and then we do calculations with ChemMap, these equilibrium calculations tend to become slower and slower as we add more elements to it. If we then add these calculations to a CFD model like OpenFOAM, the iterations of that solver becomes more and more expensive. Also with the number of system components, but also the number of cells in your mesh. And if you add all of this up, it can result in a decently sized CFD model taking even hundreds of years to solve, which is not feasible. So the current status is that it's expensive to cover the entire thermodynamic space that we have to contend with iron making and steel making. Direct integration of a CalFAT calculator like ChemApp and multiphysics software like OpenFOAM is not feasible. And we're still struggling to describe all of the material properties. Most significantly in this DRI smelting example is thermal conductivity, because slag thermal conductivity is most likely the material property that will be the bottleneck in determining the productivity of the furnace. So we need efficient material descriptions. Not just efficient, but also accurate, so that we can take these descriptions, couple it to multiphysics models like OpenFOAM, and then run digital pilot plants on our computers to make a lot of mistakes and have a lot of learnings to go forward and develop the technology. Now, the RapidThermo concept is based on the fact that if we have models and we couple them directly to a calculator like ChemApp to get material results, it is currently infeasible. RapidThermo is therefore inserted in between the models and ChemApp to act as an accelerator, to remember all of the calculations that had been done, store them as geometric objects in the phase diagram, and thereby accelerate the calculations that are fed by the or that are used by the model. Now, to be successful, RapidThermo are being built on these requirements. First of all, it must be configurable. It must be usable for any number of elements. If you add another CST file, it must be able to adapt to that. So we need a minimal configuration and be modular. It must be highly efficient, orders of magnitude of speed up, parallel execution on both CPUs and GPUs, and it must not use too much memory. It must also be accurate and credible, so mass conservation and energy conservation and controllable accuracy are really important, and it must be flexible so that multiple models can query the accelerator. There's no pre-calculation that's needed, and the entire use of the accelerator is unsupervised. So we don't need to spend a lot of costly man hours on deriving specific models for specific regions of the phase diagram. It becomes a general description. So the capabilities that we need from RapidThermo are thermochemical equilibrium, phase fractions and phase compositions must be calculated. Also properties like heat capacity and enthalpy, which are really important to multiphysics models, but also entropy and Gibbs energy need to be available. And then other properties like molar volume, which will be translated to density, viscosity, electrical conductivity, and then the critical one of thermal conductivity, as I've mentioned. We must also, with the accelerator, describe not just single phases, but also multiple phases, because the multiple phases also influence physical properties. Now, what progress have we made so far? This is just an overview. We've moved the code, RapidThermo code, over from Python to Rust, which is now much faster. We've added several material property calculations. I will demonstrate molar volume, but we've also made good progress on viscosity and electrical conductivity. We have a prototype implementation for CPU usage, but not yet for GPU usage. That we will start with a little bit later. And we have a prototype integration between OpenFOAM and RapidThermo as well. Now the example systems that I will demonstrate with are these two phase diagrams, a binary and a ternary slag systems. And the first question when you ask a piece of software to act as intermediary between you and ChemApp, then you need to know whether you can trust the results. And if you consider phase fractions and phase compositions in the binary system, you can see that all the blue regions are basically floating point precision errors. The green errors in the two-phase regions are small enough for a multiphysics model. And we do see some problems in the slag region, which is a known problem in our current prototype, which will be fixed shortly. Similarly, in the ternary diagram, we see errors between the accelerator and ChemApp calculations, which are quite acceptable when we consider using them in an open implementation. If we then look at properties like heat capacity and enthalpy, we can see here that the errors that we made in the binary system are in the order of 10 to the power of -8 or -7, slightly larger in the ternary system because of further interpolation that we need to do, but we do believe that these in the next prototype will be reduced as well. So these errors are definitely small enough for use in multiphysics models. These models in most cases use constant material properties for their entire domains. RapidThermo makes it possible to vary composition and material properties throughout the domain. This is the first demonstration of another physical property, molar volume in this case, and you can see the errors between the direct calculation of a model based on ChemApp and the RapidThermo interpolation is small in the binary case, larger in the ternary case. Again, I think we have higher order interpolation problems that we can fix in the ternary side, which will make it even more accurate. But these numbers are already quite acceptable for use in multiphysics. The elephant in the room, is it faster now? When we compare the Rust version to the to the Python version, the answer to that, it is substantially faster, roughly 100 times, or even probably between 1,000 and 2,000 times faster than what it was before. And the same goes for the ternary systems as well, where we can still improve further. Now the next steps in the development will be to test these the prototypes on simplified process systems for ilmenite smelting and steelmaking, and then to test it on the full iron making system that we are using in the GGS consortium in the Netherlands. We will also complete all our physical property implementations. Along with that will be the thermal conductivity model that one of our colleagues, Mr. Stefan Zietsman, is working on for his PhD. And finally, we will do a GPU implementation. In conclusion, as we move towards sustainability, the data and the calculations in FactSage and ChemApp will now help us to accelerate development of new DRI smelting furnace technology through large-scale multiphysics models. So we're finding a way to apply these valuable calculations and data to a broader range of problems. And it just emphasizes to me when I consider this that the understanding and the use of the second law remains key to crafting our future, a sustainable future for us and future generations. I acknowledge the contributions, the funding contributions from the Dutch Nationaal Groeifonds through our Groeien met Groenstaal consortium. We are receiving generous funding from them, which allows us to continue this accelerated development. Thank you very much.